Hi everyone. In this video, we're going to look at a technique for integrating rational functions, and that specific technique uses partial fractions. So before we get into the idea of what are partial fractions, let's review some very basic antiderivatives of some simple rational expressions. So if I'm integrating a rational expression in which I have a denominator that is a linear binomial with the 1. So for example, this one that I have here, 1 over x minus 6. X minus 6 has a derivative of 1. So it's essentially the same as if I just had 1 over x, which means that the antiderivative is the ln of the absolute value of x minus 6 plus c. If this shifts a little and I still have linear, its derivative is still a constant, but that derivative is no longer 1. So the derivative of 2x plus 1 is 2. Then I need a coefficient of 1/2 to balance that out, but I'm still dealing with a natural logarithm for the antiderivative. In a case where I have powers of linear binomials that aren't just 1, so for example, in this case, I have x plus 3 to the power of negative 2, but the derivative of x plus 3 is just 1, so it's the same as if I had just x to the power of negative 2. So in other words, I have x plus 3 to the power of negative 1 divided by negative 1, and then plus c. If this were a binomial that had a derivative other than 1, so for example, 3x minus 7 to the power of negative 2, well, I would still deal with it in the same way, except now I would have to have a coefficient of 1/3. So it would be negative 1/3 times 3x minus 7 to the power now of negative 1 plus c. And then the last one I wanted to remind you of, if I have 1 over x squared plus 1 dx, that is the derivative of the arctangent. So the antiderivative of 1 over x squared plus 1 is arctangent. Now, we can use arctangents to antiderive anything that has a non-factorable quadratic in the denominator with a constant numerator, but that requires a secondary technique in addition to partial fractions. So we'll come back to that later. For now, we're just dealing with ones where we have a denominator of x squared plus 1. Now note, I've made all these numerators 1s, but if the numerator was 5 or 7 or negative 342, the antiderivative would be the same. I would just have a coefficient of 5 or 7 or negative 342. So with those reminders, let's look at an example where we are trying to integrate 9x plus 5 over x squared plus x. This rational expression can't be simplified at all. There's no common factors between the numerator and the denominator, although that is the first thing I should check for. But what I do notice is that this denominator can be factored into x times x plus 1, which means that it's possible that this fraction resulted from adding together two simpler fractions. In other words, 9x plus 5 over x times x plus 1 could be the result of adding some fraction with a denominator of x plus some other fraction with a denominator of x plus 1. Now, a thing to note here, these numerators would both be constants, and we'll see that it works out in the algebra, but essentially, I want the denominator to have a degree that is higher than the numerators always. So what would I do to add those two fractions together? Well, I would multiply by the missing factor top and bottom in order to get them to a common denominator. And that means that these numerators would have to be equivalent. In other words, ax plus a plus bx has to be equal to 9x plus 5. Well, that means that a plus b has to equal 9, and a has to equal 5. Taken together, that means that b also has to equal 4. So I can actually express this integral. Instead of one fraction with a quadratic denominator, I can express it as 5 over x plus 4 over x plus 1 dx. And since the integral of a sum is just the integrals of the individual parts added together, and each of these fractions is quite a bit easier to antiderive, I end up with 5 times the natural log of x, absolute value of x, plus 4 times the natural log of the absolute value of x plus 1, plus, of course, c. And that is your final answer. Now, you are, of course, welcome to combine these. You don't have to, but I could write this as the natural log of x to the power of 5 times x plus 1 to the power of 4, using log laws to combine them. This is an acceptable form for the answer as well. Either one is going to work just fine. All right, let's move on to a second example here. Same idea, and notice again, the degree of the numerator is smaller than the degree of the denominator. We'll do one in a moment where it's not. But I'm going to look at this, I'm going to consider, can it be factored and simplified? The numerator isn't factorable here, so no, can't simplify in that way. But the denominator is factorable, and I get 2x times x squared plus 1. Well, that means that I can produce this fraction by adding together two simpler fractions. Some value over 2x plus some linear factor over x squared plus 1. Now, I need it to be linear. Basically, the rule of thumb is your numerator is going to be 1 degree less than your denominator. So however many coefficients that requires, that's how many unknowns you need. It would be really obvious if I tried to do this with just a constant numerator. It would be really obvious right away that it doesn't work out. That system would not be solvable. But this would have to be equal to x squared plus 4x minus 3 over 2x times x squared plus 1. So that means that a gets multiplied with x squared plus 1, and bx plus c gets multiplied with 2x. And together, those have to equal x squared plus 4x minus 3. So I've got ax squared plus a plus 2bx squared plus 2cx equaling x squared plus 4x minus 3. So looking at constant terms, that means a has to equal negative 3. Looking at the linear term, 2cx has to equal 4x, so 2c has to equal 4, c has to equal 2. Looking at the quadratic terms, I've got ax squared plus 2bx squared, so a plus 2b, and that has to equal 1. I already know that a equals negative 3, which means that 2b has to equal 4, and b therefore has to equal 2. Now when I go back to my integral, I can express it as the integral of a was negative 3, so negative 3 over 2x, plus b was 2 and c was also 2, so 2x plus 2 over x squared plus 1, and all of that dx. I'm actually going to go one step further, and I'm going to take that second fraction and distribute the division. So I'm going to now have the integral of negative 3 over 2x plus 2x over x squared plus 1 plus 2 over x squared plus 1. This now leaves me with three fractions, all of which have fairly straightforward integrals. In the first case, negative 3 over 2 ln of x, absolute value of x, so negative 3 over 2 ln of the absolute value of x. In the second fraction, you can do a u substitution if you like. You can write u equals x squared plus 1, which means that du equals 2x dx. So then I have 1 over u, so the ln of u, which is x squared plus 1. So the ln of x squared plus 1, I do not need absolute value bars. You can put them if you want, but x squared plus 1 is always positive. And then plus 2 times the arctangent of x, plus, of course, c. You can combine those two logarithms if you want using log laws. I'm not going to bother because I can't combine them with the arctan anyway. So here is what I get. All right. I promised you an example where we had a numerator that was higher. So we have to start a little differently. And essentially, we're going to start by dividing this out. So I'm going to turn this into a quotient and a remainder, which will still be over the fraction. And then I will have, in my remainder, a smaller degree in the numerator. So I'm going to divide. And I'm going to use long division because I'm dividing by something that's not linear. So I have x to the power of 6 plus 0x to the power of 5 plus 0x to the power of 4 plus 0x to the power of 3. Lots of zeros in here. It's kind of tedious, but it is the way it has to work. And I'm going to divide that by x to the power of 4 plus x squared. Now that denominator is factorable, and the factors will come in later when I'm finding the partial fractions, but for this first part, I'm just dividing. X to the power of 6 divided by x to the power of 4 is x squared. So what I end up with is x to the power of 6 plus x to the power of 4 which when I subtract, I now have negative x to the power of 4 minus 2. Negative x to the power of 4 divided by x to the power of 4 is minus 1. Negative x to the power of 4 minus x squared. When I subtract these, I end up with x squared minus 2 is now my remainder, because this now has a degree less than the original denominator. All right, so expressed as the division here, x to the power of 6 minus 2 divided by x to the power of 4 plus x squared is x squared minus 1, plus x squared minus 2 over x to the power of 4 plus x squared dx. This fraction part is where I can use my partial fractions. So right here, I can do partial fractions. Factor the denominator, it's x squared times x squared plus 1. And that then allows me to figure out my partial fractions. Now, this gets a little bit gross because there are actually 4 fractions that I have to create here. So the results of the addition of a over x plus b over x squared plus dx over x squared plus 1 plus, oh, I might as well use a c. I don't know why I suddenly skipped to d. So cx over x squared plus 1 plus d over x squared plus 1. What I've done slightly differently in this question is I've already split up that linear over the x squared plus 1. And I want you to note what I've done here with the x and the x squared. It isn't always necessary to do that when you have a squared factor, but it's often enough necessary in order to make the coefficients work out. But basically, when I have a squared factor, this is typically what we do. So if I have x squared, I'm going to have one fraction over x and one fraction over x squared. When I do this partial fraction, you are going to see that in this case, it wasn't 100% necessary. I could have just done b over x squared. The reasons why are a little complicated and beyond this course, but just as a good practice, and if you want a little more detail on it, you can certainly look in your textbook. As a matter of practice, when I have factors that are squared, I'm going to repeat fractions like this. All right, so now for a common denominator, the a would have to be multiplied by x and x squared plus 1. The b would have to just be multiplied by x squared plus 1. Cx would have to be multiplied by x squared, and d would have to also be multiplied by x squared. Now, in this case, it becomes fairly obvious pretty quickly that we don't need the multiple fractions, the a and the b, and that's because in this instance, my numerator doesn't have an x cubed term. So my numerator does not have x cubed, but it could because my denominator is x to the power of 4. So that's usually why we need to repeat factors. When I distribute these things, I have an ax cubed and a cx cubed. So I have a plus cx cubed. On the x squareds, I have bx squared and dx squared. So b plus dx squared. Linear terms, I just have ax. And constant, I have b. And together, these have to equal the x squared minus 2. That is my original numerator. So there's a couple I can jump to right away. Looking at the constant, b equals negative 2. I don't have a linear term, so a equals 0. A plus c has to also equal 0, since a equals 0, c equals 0. And b plus d has to equal 1, while b is negative 2. So that means d equals 3. So now handily, 2 of my fractions are zeros, so I don't really need to worry about them at all. So my derivative now, or antiderivative, the integral that I'm taking, it's the integral of x squared minus 1 minus 2 over x squared plus 3 over x squared plus 1, all dx. And each part of this is now ready to be integrated. So I've got x cubed over 3 minus x plus 2 over x plus 3 arctan x plus c. So it took us a while to get there. To recap, we had to divide first, then we had to work out our partial fractions, and finally we could do our antiderivative. All right, there's a lot there. Let's go on to another example. This one is actually simpler than the previous one. It's just the factoring is a little bit more complicated, but I want to make sure that I check to see if it can be simplified first. So the numerator in this instance is not factorable, so it can't be simplified as a simple rational expression. The denominator is factorable, and I can factor it by grouping. So I've got x squared times x minus 2 and minus 1 times x minus 2. So that's x minus 2 times x squared minus 1, which is x plus 1, x minus 1. So 3 linear factors, which means I've got 3 fractions being added together. I have something over x minus 2 plus something else over x plus 1 plus a final constant over x minus 1. That all has to give me the x squared plus x minus 3 over x minus 2, x plus 1, x minus 1. Each of these numerators is going to have to be multiplied by 2 factors. So a is being multiplied by x plus 1 times x minus 1. I'm just going to go ahead and distribute that, call that x squared minus 1. b is being multiplied by x minus 2 times x minus 1, which is x squared minus 3x plus 2. And c is being multiplied by x minus 2 times x plus 1, which is x squared minus x minus 2. My quadratic term, therefore, is a plus b plus c. My linear term is going to involve negative 3b minus c. And my constant term is going to be negative a plus 2b minus 2c. So a plus b plus c, that's my quadratic, that has to equal 1. Negative 3b minus c, that's my linear, that has to also equal 1. And negative a plus 2b minus 2c has to equal the constant term, which is negative 3. So I have a system with 3 variables. Not super fun to solve, but using skills you've learned before, I'm going to add the first and the third equation together. So the a's will cancel, and I get 3b minus c equals negative 2. Combining that with the second equation, so adding those two together, the negative 3b will cancel with the 3b. I get negative 2c equals negative 1. So c equals 1/2. We can reverse engineer this, plugging that back into the second equation. If c equals 1/2, then I plug that in to the second equation, and I get that b equals negative 1/2. And then finally, since a plus b plus c has to equal 1, a equals 1. All right, we've got our fractions now. These ones, fortunately, are going to be easy to antiderive. I've got 1 over x minus 2. I've got minus 1/2 over x plus 1. And I've got plus 1/2 over x minus 1. Each of these is just going to be a natural log. So I've got the natural log of the absolute value of x minus 2 minus 1/2 times the natural log of the absolute value of x plus 1 plus 1/2 times the natural log of the absolute value of x minus 1 plus c. You can leave your answer like that, or if you wanted to express it all together, you'd have x minus 2 times the square root of x minus 1 divided by the square root of x plus 1 plus c. Also an acceptable form for your answer. All right, so quite a bit of algebra involved in these questions in terms of figuring out your partial fractions. And there's some weird little nuances and tricks here. You can practice them. There's the questions in Reed 17.4. There's questions in Stewart 11.6. There's also a partial fractions worksheet in D2L. The very last question, number 10 on that worksheet, requires trig substitution, which we obviously haven't done yet. So we can come back to that question a little bit later.